Alright, section 2, part 2, we are going to get some math done. So get your pencil ready. So last time we are trying to see how can we get some nice, some useful information out of the sample parameters. And now we are going to talk about the confidence interval. This is not the most important part, like the very first concept that is applicable in theory. I don't know what to say about it, but if you study just the statistics, like how to make nice graph, okay, that's good for you. That's one thing you can do. If you just study math, the probability side, then again you can have fun with all the numbers, variables, expected values, then that's good for you. But if you have to like combine these two and get something that can say something about the sample, then we have to get this thing first. Like it's the first thing we can get. So before, I should not show too much text. So what we are trying to do here, we are trying to estimate the population mean mu using the sample mean x bar. And we get x bar. We want to like kind of like manipulate, put that into some formula to estimate the mu. Right. And what are the formulas? Then here's the formula. Right. So as I said before, the number is not going to be exactly 1. Like if the sample mean, the average is 10, you are not going to say that okay, the population mean is also exactly 10. It's going to be 10 plus or minus some number, and that number here can be computed here as follows. Right, x bar, like the sample average, plus or minus that amount by 1.96 times sigma divided by square root of n. But also adding that, we are 95% confident. Right, this is the formula for a 95% confidence interval for the average. So we are saying that the average is between these two values, between that average plus some amount and minus some amount. Or we can say, okay, that mu is inside this interval. So we are going to get x bar here. So we have this formula here, 1.96 times sigma over square root of n. So that's gonna be this and that, because it's plus or minus. This here is this thing here is 1.96 times sigma over square root of n. Oops. Okay, now that means now. Right. So what we are saying is that we believe that the actual mean, the actual mu, right, is somewhere inside this interval. We don't know where exactly, of course we can't, right, but we are pretty sure it lies inside this interval. It may be exactly x bar, right, if we are very lucky. It may be x bar plus some amount. It might be x bar minus some amount. But what we can say is that we are 95% sure that's the mu, right? The mean, the thing that we are going to estimate, is inside this interval. It's between these two numbers. And what we need here, we have 1.96, which we will explain in a moment why we get that number, times the sigma. Right? So the sigma is the standard deviation of this population, and we have the square root of n, and n here is the sample size. So before we go to compute, let's just look at this formula for a moment. Like if you study math or like anything, if you want to be critical, critical thinking, you have to ask, okay, what can we say about just this formula? Like, okay, we can say it's symmetric, like it's centered at x bar, and we add and subtract that by the same amount. Right, so x bar is gonna be in the center of that interval. Then what else we can say about these numbers? Right. We can say that, okay, sigma is on top. That means if we increase the sigma, like if the sigma gets larger and larger, then this whole number, if that thing is larger, then this whole number is also larger, right? And if that thing is larger, then that means the interval itself is also getting larger. If sigma is 1, you get that. Maybe you get that interval. If sigma is 2, you get that interval. If sigma is 3, you get that interval. 4, 5, 6, and so on. And does that make sense? By the way, sigma, the standard deviation measure the spread. If sigma is high, then we know that all the data are spread out, like they have like a flat curve. If sigma is small, then we have like a tower. If sigma is large, we have a flat curve. And that agrees with our intuition about the center and the spread. Right? If sigma is larger, then the data or the points are spread out. That means the mu, the actual number, is less likely to be around that point. Like it might spread out further and further because we have a large curve. And on the other hand, what about that one? In the denominator, we have the square root of n. So that means if n is larger, then of course square root of n is also larger. If n is larger, right, then the square root of n is also larger. And the reciprocal, when we flip that, when we take the inverse, right, that means this whole thing will get smaller, like that. The number at the end will get smaller. Is it good or bad? Of course it's good because we want to estimate the mu, right? And for an estimator to be good, then it should be close to the actual number, to the sample that we have. Like if we get a pretty slim, interval, let's say the size is only like 0.001. What it means that we are very confident that the number we got from the sample is very, very close to the actual number, the actual mu. Okay, so that's a good thing, which means we should get a large number, a large sample size. Then we should increase n if we want to get a better estimate. So we want a better n. And again, that follows the intuition or the set of data. Right? The more data we have, then the more we can say about it. The more we can be confident about anything. If we get just one ball, then we can say nothing about the whole bag. But if we have 100 balls, then we can get some idea, a better idea of what is in the bag. So let's this is just a number, and we are going to tie this back to the standard normal distribution in a moment. But the idea is this: if what we have here, like if the mean, and the formula is cut off somehow. If the mean, if the sample mean is here, let's say it is 10, and if we know that the distribution of all the means is normal distribution, then we can draw this nice curve, right, and get some information about where the points are, how high the curve is, and so on and so forth. So now what we are trying to say is that we don't know exactly what the mu could be. Like it could be all the way here. If we are unlucky, it could be very close here. Right. See, even if we cannot say exactly about where the mu is, then we can use the probability, right, to determine something. Now we can say something about the probability itself, right? And we can compute that probability from the table, the Z table, or whatever app you have here. Right? The goal is we want that probability to be 95% or 0.95. We want to be correct most of the time. And by most, we usually pick like some random number, 95%. If you want to be correct 95% of the time, then you want to get the area of 0.95 here under this curve. If we can get a point such that the areas between these 2 points is 0.95. Then that means we have 95% chance that if we pick any random number in this curve, then that number will lie between the interval we pick. Okay, so I mean if mu is anywhere in this curve, then we have 95% chance that mu actually lies in the range that we pick between the left and the right side. I think we're gonna have that in a moment. But okay, let's just compute something. So suppose we use a sample size of 100. So we pick 100, whatever, and we get a sample mean of 122. Let's say that's the height of students or something, and the average is 122. So suppose that the standard deviation or sigma here is known to be 20. We are asked to find a 95% confidence interval. So let's just do that. So what do we need here? We have n, right? We have x bar, we have sigma. Oh, we actually have everything already. So let's just use the formula we have above. You can scroll back, or I'm gonna write one for you. Is x bar like plus or minus 1.96 times sigma divided by square root of n. Okay, that's the formula for 95% confidence interval. And we can simply compute that with all the numbers we have here. We have x bar here, like it's 122. Let's use colors because I can. We have 1.96, that's a constant. We have sigma to be 20, so that's 20. We have n to be 100, so that's square root of 100. Now we have all the numbers, which means we can simplify. We have 122 plus or minus 1.96 times 20 divided by square root of 100. Sorry about weird light. It's dark, so I have to use external light. So that's 20 divided by 10. That's gonna be 2. So it's 122 plus or minus 2 times 1.96. We get 3.92. And that's done. Right. We get a number. What does that number say? It says that the population mean of mu is between these two values, like 122 plus 3.92 and 122 minus 3.92. We can now see that the mu, we are confident, we are not 100% sure, we are confident that the number lies between 125.92 and 119.08. Or if you want to express that as an interval in that, we have 119.08 to 125.92. Done. It means, okay, we from what we have here, like from this table, we have that average is 122, but it's not going to be exact, so we adjust that. We add some amount to each, so we add subtract some amount, and now we can be confident that the actual population parameter mu is going to be between 119 and 125. And again, we have to add that 95% confident. Oh, sorry about the handwriting. I have to remind myself to write more slowly. Okay, 95% confident. Okay, that's simple way to just use this formula. I just plug in that thing, x bar, plug in sigma, plug in n, and you get one single number. So how do we get that formula in the first place? So oh yeah, well, I go back and forth. Like, but that's what is that formula? Like we have, that's the x bar, the point estimate, like the sample parameter x bar we get from the sample size that is small. So that's one thing. We have the reference point, right? And we have plus or minus some. There are like different ways of saying that, but let's me use what agrees with the textbook I put there. Let's say this whole thing in the back is the margin of error. Before we have 1.96. Right. That number corresponds to the case when you want to be 95% sure. If the number changes, if you want to be only like 50% sure, or if you want to increase that to be 99% sure, then this number here, the multiplier here, is gonna change also. Right, so that we have that estimate plus or minus some error, margin of error, MOE. And our task is to determine how to catch that error. And this is the mathematical way to get that error. So the problem here, we can translate that into math equation, which is this equation. Like this equation asks the probability that the mu is not too far from x bar. That's the same image as we have, and we want to find the probability that the mu is not too far from x bar, and we want that probability to be 0.95. We have to have pretty high chance that it's not too far from the x bar, and the task is to find e, to get the endpoints of the interval such that the area inside this range is about 0.95, and that brings us back to this image. Our task is from x bar. We want to find these two endpoints that contains 0.95, contains 95% of the total area. And that's the math part. And how do we solve this problem? And we have to go back to last lesson. minus, and ask, okay, how can we transform that to the standard? So some question about the standard. Normal distribution. Because if you use the standard normal distribution, then that number can be, we can look up that number and compute for the value e, and for the value for the margin of error. And so we want to transform that into the standard normal distribution. Okay. And from last time, the way we transform it is to use this kind of formula. It's x bar minus mu divided by sigma over n. So we now transform x bar, the thing we have here. Oh, sorry, we transform mu. We know x bar already, so we transform mu into z. Okay. We change from the distribution about mu to z. Right. From that formula. Right. And from that formula, then now we ask, okay, what value of e that we bound the two ends of the curve to 0.95. So let's look at not this one. It's this one. Now we have you can use. Oh yeah, I should have added that. So we use the standard normal distribution curve here. Okay, so that's the curve. Maybe the average, the mu is 0. The standard deviation is 1. So we can use this formula to compute the value of x. You can either input x, right, and get the area, or in reverse, you can put in the area and get the value of x. In this case, we want the area. Again, we want the area. We want the probability to be 0.95. So we put 0.95 here, right, and then just click outside, and now it gives you the value of x. And now x has to be 1. X is about 1.95996, which we're gonna use just 1.96. And so that means if these two endpoints are about 1.96 and minus 1.96, then the red area, right, the total area here is between 1.95. Or again, we can translate that back to the vocab of the probability that if we allowed the error to be about 1.96, then we have 95% chance to be correct. So let's get back here and remove that thing. Yeah, Chrome. Right. And once we have computed all of these things, now we're gonna get that this thing here. That's why we get that sigma and square root of n, because that's the formula for transforming one normal standard, from normal distribution to the standard normal distribution. And 1.96 is a number from the lookup table, from the C table. If you want to change the number 95 to other numbers, then we are going to use this formula here. So what we change here is just that single number. Instead of 1.96, then we just put z of alpha divided by 2, where that alpha now corresponds to the confidence level that you choose, and we express that as 1 minus alpha, because alpha is going to be small. In the standard case, we have this as 95%, right? So it's 0.95. We want 1 minus alpha to be 0.95. That means if you do some math, then alpha is 0.05. And in this formula, we use alpha over 2 instead. So alpha over 2 is going to be 0.025. Okay, and now you may ask, why do we use alpha over 2, not alpha itself? Right? Because if we go back to this curve, right, we want the area, we want this area to be the number we want, which is 1 minus alpha. So we want the other part of this curve, like the outside, to have the rest of the area. If the area inside is 1 minus alpha, then the area outside this curve is gonna be alpha, because the total area. We use the fact that this is a distribution function. The total area is 1. Right, so if this whole thing in the middle is 1 minus alpha, then the rest is alpha. And since the rest we have 2 parts, right? It's not just 1 part. We have 2 parts, and we know that the size of each part is equal. Why? Because we choose these 2 points to be symmetric. And now this is useful to be symmetric. If it's symmetric, like if we choose points to the left and to the right at the same distance from the center, then the area of the outside area of each part is gonna also be the same. So since if you know that the total area of this blue part, right, if these 2 parts has area alpha, then one of them has to be alpha over 2. Okay. So now we want the area of each part to be alpha over 2, alpha and a half. Then we want to find the point z. In this case, we specify that to be c of alpha over 2. Okay. We want this part, we want this area here, like, to be alpha over 2. Which means, if we write that as a math, we want the probability that z greater than c alpha over 2. We want that area. That area is this probability, and that probability we want that to be alpha over 2. And that means we can now use the table again, use the C table to find the part where that is true. So in our example, if we want that to be 95%, then I'm repeating what we have. For we want the outside to have the area of 0.05. That means half of that has to have the area of 0.025. That means this one. And we want to find a point z of alpha over 2 that has the area of 0.25. So let's go back to that. Oh, I have to do this first. Show. Okay. Now we want that area to be. Oh, it's already here. We want that small area to be 0.025. If we enter or click outside, 0.025, and then again we get the result that we want, which is a point x or c. Close Chrome. So that means we can use the C table to compute the point, the exact point to cut off, and that point is what we put here in the formula. You don't have to remember if you understand the process, right? You want the area to be 1 minus alpha, so that means the area here has to be alpha over 2, and from that you can use the f I give you to compute the point here. Then if you follow the process of these 3 steps, then you can get the value of set of alpha over 2. If not, then you have to memorize. Okay, we need 1 minus alpha. We have to divide that alpha by 2, and then we have to look up. That also works, but it relies on you being able to remember the whole formula. If not, then just do that. So let's take a look at one example. Suppose we have a sample size n equals to 40 with a sample mean of x bar 175. Again, that looks like a height. and with known standard deviation of 20. Now we want to find a 90% confidence interval. Last time we did 95, but if you want to find 90% instead, so let's do that. Right, so I'm going to do it with the graph, without the formula. So we want this area, right, to be 90% or to be 0.9. To be 0.9. That means we have like 0.1 left, right, for the rest of the graph. And since we have two parts which is the same size, that means this part is 0.1/2, like 0.1/2, which is 0.05. Now we want to find a point, this point, such that the area to the right is 0.05. So let's use that and put in 0.025, and okay, now we have 1.64. That means this is about 1.64. So now we can compute that whole thing. Oh, sorry, it's plus minus, like whatever that number is, times sigma divided by square root of n. So we have x bar here, 175. We have that number which we just got, which is 1.64. Oh, sorry, I forgot to turn this off. Okay, put this off. That's x bar is 175. Z, the value, the point here is about 1.64. Oh, that should be approximate. 1.64. Sigma, do we have sigma? We have here 20. And do we have n? Yes, we do. We have square root of 40. And then we can just use that to compute the exact number. Give me a moment to. If you also download the slide, the handout, you should get the number also, but I don't have it at hand, so I have to go and open it. And that number is 6.2. Right, that's about 6.2. So that means we are now we have our interval, our confidence interval. So in the end we can say that okay, the mu that we want to estimate, the value of mu here should be between this the left side is 175 minus 6.2, which is 0.88, right, to that number 175 plus 6.2, 181.2, right. And then we have to add with 90% confidence, and that's the answer. Or actually you can just answer with that interval, because we already said that we want the number to be 90. But like if you just only see the interval, then you have to also know how confident you want it to be. Like with 90% confidence, the actual mean, the population mean, should be between 168.8 and 181.2. And that's done. So now what we have to compute? We have to compute just only here, this one here, by from using the curve, the number, whatever. If you want to actually use the formula, then sure, you want that 1 minus alpha, that should be 0.9. Right, from formula, the confidence level is 1 minus alpha. If that is 1.9, then alpha is 0.1. So alpha divided by 2 is 0.1 divided by 2 is 0.05, we are going to get the same number here with the curve. But if you start from the formula 1 minus alpha, then you have to remember, okay, it has to be 1 minus alpha, not alpha minus 1. And then you have to remember to divide by 2. If you don't want to do that, then just make sure you draw this curve first, and everything else will follow from that curve. So now let's try. This is we use the same numbers. Like the sample size is still 40, the mean is still 175, the standard deviation is still 20, but we now increase the increase the confidence level. Now we want that to be 95%. So then again we gonna have that formula times sigma divided by square root of n. If we think about the curve, then we want that this area, the area in the middle, to be 0.95. That means we have 0.05 left for both sides. So we have to put half here and another half here. And 0.05 divided by 2 is 0.025. And then again you can use the f to determine. If you want that area to be 0.025, then that point has to be 1.96, which is the same as what we have at the beginning, because that's 95% confidence interval. So also we have x bar to be 125 plus or minus 1.96 times 20 divided by square root of 40. Just put all the numbers in this formula, and then we get x.76. What did I say? Did I say x.76? Yeah. So again we get a nice interval, which is 6.34 and 183.76. Now we get the 95% confidence interval. And just to make sure you get that, you should add that this is 95% confidence interval. Like the formal term, or not formal term, it says that we are 95% sure that mu is in this interval. The formal and not formal way of saying. So now we get the number. And again, lastly, we have this again the same n, x bar, and sigma. But now we increase the confidence level to be 99. So that's gonna be the same setting, like x bar plus or minus the confidence level times something. So we want that error to be 99 or 0.99. We want that alpha to be we want that error to be half of that. Right, now we want to find that thing. So let's use what we have here. We want to put in 0.05 and then we get 2.6, about 2.57. Not that one. I want that to be up and that to be down. Okay, now we don't have to worry about the nice. So again, we have 175 plus or minus that number, whatever it is, 2 point something. 2.57 times 20 divided by square root of 40. I think there's a typo in the slide, and we fix that. And that happens to be 11.49. Right, so now we have that 163.51 and 186.49. Now we get a different interval. Okay. But now we have 99% confidence interval. What does it mean? It means we have a 0.99 chance that the actual parameter mean will be in this range. So that's it. Just put in that side here. So now we have three numbers, right? This 1.168. If the confidence level is 90%, then we have plus or minus 6.2, maybe something like that. If we increase the confidence level to be 95%, then that number increase to be 8.76, and if we increase that to be 99%, 11.49. Right, so to summarize here, okay, for 90% we have point plus or minus 6.2. For 95% we have the error as x.76, and for 99% that becomes 11.49. Right. And all these numbers are different. None of them is correct or wrong or best or worse. They are just different. But as you can see, if you increase the confidence level, right, from 90 all the way to 99, then the length, the size of the interval itself also increase. Right, now we first have 6, and then we have 8, we have 11. And does it make sense? You have to ask, does it make sense? And the answer is yes, because if we want the area to be 90% or 0.9, then we get some number. And that's 6.2. If we increase the size, if we increase the area, and now we want the area to cover 95%, then that point here, the point that we choose here, has to be further away. In this case, it is 8.76, and now we add some area here. And then finally, if we increase that area to be to cover 99% of the curve, then that point again has to be pushed further. Now we have 11.49. So the more confident we are, the larger the interval is. And since the interval is larger, then we are less sure about the exact value. The higher the confidence level is, or the number is, then the larger the interval becomes. So again, we have to ask, is it good or bad? Is it good or bad to have a large interval? The answer is bad, right? Because we want to narrow down. Like we don't want to say that it's between minus 100 or plus 100. Like again, that's not a useful information to know. To be useful, we have to have a narrow interval that we can work on. So if the interval is large, then it's bad, right? So if we don't want that to be bad, then we can make the interval to be small, right? So yes, we say that okay, the large interval is bad, small interval is good. So why don't we just make the interval to be very, very small? Right, in this case, we can make that interval to be very, very small, like 0.01. But the problem is we have a trade-off here. We have small interval, but our confidence level drops down by like a large amount. Before we can say something about, we have 95% confidence. Now we have small interval, but only 10% confidence. Okay. That means okay, we have a very nice and small interval. Okay. But that interval only contains like 10% of the graph. Okay. Most of the graph are outside this interval. 90% of the graph are not in this interval. So that means we have a very large chance that the actual number is outside. Right? And if that number is outside, then that means we fail, right? We want to guess that number. But if that number is away, is further from our estimate, then we fail to estimate that number. So that means large interval is bad. Small interval is also bad. What do we do here? Right? Panic. Oh. What do we do here is, of course, if it's bad to be large, if it's bad to be small, then we want to find the right balance between large or small. We want to get somewhat decent interval, and we want to get somewhat decent confidence level. We can get the best of both worlds. We can only get like some decent level of both, right? And that's the reason why we pick number 95, because 90% looks good on paper, right? We think okay, 90% is good enough. 95 is even better. So 95 is good. And it's not the best, but it's good. But it also gives a not too wide interval. Notice I'm not saying it's narrow. I'm saying it's not too wide. So we also have a decent amount of confidence. We also have a decent length of the interval, that it is not too large or too small. And that's the reason we could pick number 95. And of course, you are free to choose any other numbers if you know what you are doing. Some different areas, like for the basic course, we get number 95, but for different areas, the numbers varies. Maybe you want 99, maybe you want 90. As a rough thumb, just pick 95, and that also will give you the number of 1.96. That's kind of convenient to remember because it's about to like closer to. You can do it in your head. Right? Okay, this number is 2 times whatever. Not too bad. Okay. And oh yeah, again this is swap, right? And last note is that since the area, like we look at the area, right? We want to have some area here, right? And something else there. You may ask, can we get all the areas? Like can we get 100% confidence in this range, right? The answer is yes, we can. But if everything is here, then that means nothing is on both ends. Right? If it's 100 here, then nothing's on both ends. But since this curve continues to infinity, right, on both sides, right? If we want the right side to be 0, then that means we have to increase both points to infinity and minus infinity. So if we want to say something that we are 100% confident, then that means both these points have to be infinity and minus infinity. Is it possible? And yes, of course, but that means the number mu itself, like the actual value of mu, can be anything, right? If you increase both points to infinity and minus infinity, then that means the number can be anything, and that information is of course useless, as I suggest at the beginning of the class. Like if you say something between 0 and 100, then sure you are correct, you are 100% correct. You are always correct. But you are not saying anything useful. So you can say 100, but that doesn't say anything. Or on the other hand, if you have to pick some point here, right? If you want these both endpoints to be some number, maybe like even 100, right? Then it means the area is not 100%. It's not 1. The area is gonna be like 0.9999995 or whatever. But that means we cannot say that we are 100% confident that we get this range. Yeah. So we either say we are 100% confident that it can be anything, which is not useful, or we can say if we put endpoints, if we get an interval, then we can say only like some percent, so it's not 100. The percent, the confidence level is always, it's gonna be less than 100. So yes, we cannot say. So what's the takeaway from this? The takeaway is we want to get some good balance of these two numbers. We cannot get both the high percentage and we cannot get both small interval. Okay, that's the break. Yeah. So we are going to continue to the last part of this lecture.